there is really a need to incorporate the viscous flow into the boundary layer solutions, because otherwise, whenever the boundary layer separates, you have no solution anymore. Okay, so to discuss this, let's start again with these two equations, okay, and discuss how we actually are going to implement them. And so before we actually start to implement them, I'm going to tell you there is a problem in this minimum h, right? Minimum h star. Because if you look at this equation, especially look at the second equation, if UE keeps decreasing, let's say in an adverse pressure gradient, so dUE dx is going to keep being negative. And my h star has a definite minimum, right? My h star, no matter in turbulent or laminar boundary layers, it can only go as low as this point. I mean, this point is in laminar boundary layer. In turbulent boundary layer, there is also a minimum that you can go below. So what can you do? So that means as h star reaches that minimum, you can't really solve this equation anymore if dUE dx still is negative, right? And if it is still negative enough to overcome these terms, the other terms, then you can't solve the equation anymore. So what can we do? What does the actual flow is going to do? Just to think. It separates, right? But after it separates, what happens to this equation? Is it necessary that this thin layer equation is no longer valid? I mean, it's true if it's a massive separation, right? But if it's a, can it still be a small scale separation that is relatively thin, relatively flat, like a laminar separation bubble? What actually happens in that case?
I mean, the flow reattaches soon, right?
The flow reattaches soon, but like before the reattachment, how would the h star stop decreasing? So let's say I have a boundary layer. I have a boundary where the flow at this point is just about to separate. Okay, so my h star at this point is reached minimum. In the physical flow, we know that, okay, the streamline here separates and there is a separation bubble going on into here, and at some point maybe it transitions into turbulent, reattaches. Let's not care about that yet. But if you look at the velocity profile here, we know it has a profile that is like that, right? There is a clear defined h star here, right? If you look at this profile, and that h star can only be greater than the h star here, right? So what happens to the second equation? What is making h star increasing as opposed to further decreasing? Does h becomes less than 1? Actually, no, because h, so this region is the separated region. So for separated flow, h is usually typically a lot larger than non-separated flow. Okay, so you can think of the that's because if you look at a separated profile, the displacement thickness suddenly is going to increase by a lot. What happens? Okay, yeah, the displacement thickness is suddenly increased a lot because the whole separated region is going to be added into the displacement thickness, right? So if you look at the ratio of displacement versus momentum thickness, it's going to be increased by a lot. Momentum thickness may not be increased by a lot because in this separated region, the velocity is usually very small, right? So you have this 1 minus u squared term in the momentum thickness equation that didn't really add up much into the momentum equation, into the momentum thickness. But the displacement thickness is 1 over u, and u becomes negative. So that adds to the displacement thickness a lot. So it's natural. It's not just by coincidence that in separated flow, the h, the shape factor, is very large. Okay. due dx. That's right. Exactly. So that's a very good point. Whenever the flow separates, look at what the streamline is doing. Whenever the flow separates, it kind of creates almost an artificial blockage on top of the boundary, on top of the wall, right? So this fluid, this amount of separated fluid, can be considered just as a bump added onto the wall. Okay, and that bump onto the wall makes the adverse pressure gradient no longer adverse, because think of a wall like that. Now you originally have a wall like that, and suddenly you add a bump. The streamline has to, if the streamline originally goes over the wall, now it has to do this. So in this, in here, basically you're creating a high pressure region here because you have to push the flow to curve upwards, and that actually prevented this due dx to still be negative. Okay, so this brings us to the realization that in order to further solve this equation, even after separation, there is a need of incorporating the inviscous flow, the external flow outside the boundary layer, into this consideration.